Annuities with payments in arithmetic progression. We see the new symbols that we're going to be using. These are all net present value symbols. And the annuity is on the timeline. So our first payment is going to be P at time 1. We're going to increase it by an amount Q. So our second payment will be P plus Q at time 2. And each subsequent payment we're going to increase by Q as well. So there are our n payments on the timeline. The symbol for the net present value at time 0 is given by this I sub PQ. And the student may want to pause and verify that what I'm calling A here is indeed the net present value of the payments on that timeline. So assuming you have verified those, or that is indeed the present value, where V, the powers of V are the discount factor, I'm going to multiply that equation on both sides by 1 plus I. On the left side I get 1 plus I times A. On the right side, multiplying by 1 plus I just brings the powers of the discount factor down 1 each time. So my term PV becomes P. My term P plus QV squared becomes P plus Q times V, and so forth, all the way down the line. Once I've made this multiplication, I'm now going to subtract the first equation from the second equation, so that on the left sides of the equation, my A's will subtract away and I'm just left with I times A. When I do this on the right side, I have P here, and then I'm going to subtract the P times V, subtract from this P times V the P times V above, and they cancel. The P times V squared in the second equation subtracts away from this P times V squared, and they cancel. The P times V cubed here has another P times V cubed down here in this term. They subtract away. The P times Vn minus 1 down here subtracts away from the P times Vn minus 1 in this term, preceding the last term. And the last term, there's nothing for this P times V to the n to subtract with, so it gets left, P times V to the n. And then if I look at my Q's, I have Q times V here in the second equation, and I have QV squared times 2, and I subtract one of those away from up here to get just QV squared. I have 2 QV cubes, and I'm going to have 3 of those in this expression, so I'm just left with QV cubed. I continue that throughout my expression. Again, this QV to the n minus 1, these will subtract away and just leave me with one of those, QV to the n minus 1. And then this term here just comes down. I'm subtracting it, so it's minus n minus 1 QV to the n. Okay, so a little bit of algebra you need to verify. In the next line down, we'll just do a little simplification. We'll factor a P out of the first two terms. We'll rewrite our QVs. And then this last term, I'm going to take a minus QV to the n. That becomes a plus QV to the n. And I have minus n QV to the n. So in other words, I'm just going to multiply through by QV to the n through that parentheses there. And finally, on the last line, I'm going to divide both sides by I. And before I divide the rest of this expression by I, these n terms can be combined using an annuity immediate symbol, Q, A, N. Then I have, of course, my last term, minus n, QV to the n, and all that gets divided by I. So finally, I see that 1 minus V to the n over I here becomes this annuity immediate symbol in front of the P, and the second term here simplifies by factoring out a Q. So the formula in the box is the final formula for my net present value of this arithmetically increasing annuity with initial payment P and amount of increase Q. We can work all the problems in this section with this formula, most all the problems, but it is handy to get to know some other formulas and at least get to see the relationship between the other formulas and this one. And so we'll discuss them here on this page and the next page of the notes. The first modification would be if we moved all of our payments in time, where the first payment was at time 0 rather than time 1. So we have an increasing arithmetic annuity due, and that formula is in the second box. And of course we can always get that by multiplying the formula in the first box by 1 plus I. So again, we don't really have to memorize this formula, but it's easily derived, or you can just take the formula in the first box, multiply by 1 plus I, and you'll get the value for the annuity due. Another formula that is very basic that we use a lot is when the first payment P is 1 and the increasing amount is also 1. And we give that a special symbol, I, capital I, A. So this is an arithmetically increasing annuity with initial amount 1 and increasing amount 1. So if we plug 1 in for P and Q above, we get AN plus AN minus NB to the N over I. And then if we multiply this by I over I, we can combine the first two terms by factoring out the AN. So again, if you don't see that, pause it. Make sure you understand how we went from here over to here. Now this is how I would remember the formula, but your book will rewrite it by rewriting this 1 plus I annuity immediate as an annuity due. So this is how you're going to see it in your book. And that's okay. Nothing wrong with that, except that it's kind of confusing to see the umlaut above the A when this is really an annuity immediate here. But it's just a calculation. It's in the calculation of that value. Now the corresponding annuity due, increasing annuity due formula, of course we just multiply by 1 plus I times the increasing annuity immediate formula. And when we do that, we would just get what? 1 plus I. And I like to use a formula that I remember. I don't like to put the due symbol above. 1 plus I times this symbol. And the 1 plus I can actually come down to the denominator. In this way, and then this is the D. So that's how we're used to seeing the relationship between an annuity immediate and an annuity due formula. The denominator changes from I to D, and it happens again in this case. Now, another formula that's really handy is if we go back up to that timeline above, the very top of the page, we want to value our annuity at the time of the last payment. Then that means we're accumulating all of those payments to the end, and we use the S symbol, or I sub PQS. And so what we could do is just take and bring forward in time my present value of the annuity immediate by compound interest, by multiplying by 1 plus I to the n. And so we don't really need to memorize this formula, but if you want to see how the formula comes about, you take your 1 plus I to the n, you're multiplying by what? PAN, and then each term in the numerator gets multiplied by 1 plus I to the n as well. See if I can get that in there. And this 1 plus I to the n times an gives me the Sn here. 1 plus I to the n an gives me this Sn here. Then the v to the n and 1 plus I to the n cancel, and so I just get n. So you see where the formula comes from right away. So whether you want to remember and use the formula in the box, or just bring the annuity immediate present value, net present value formula forward in time to the time of the last payment by multiplying by 1 plus I to the n, it will be your choice. And in like manner, we can do this with the net present value when the annuity payment, when the beginning payment and increase amount are both 1, and we can simplify that formula. So we have what? Sn plus Sn minus n over I. Again, we can multiply by I over I. We get 1 plus I Sn minus n over I. It's a fairly simple formula for the accumulating, that increasing arithmetic annuity. And one thing I want to do is to look at example 3.9.8 in the book. So we can go ahead and do a calculation. In this example, we're going to deposit $2,000 on our 19th birthday, annually increase the amount of the deposit by 500, and make those deposits on the future birthdays. The last deposit on the 35th birthday, we want to calculate the net present value on the 18th birthday, and looks like we want to use 4.2% interest. Okay, so if you draw a timeline to look at these, 18th birthday, that's where I want the net present value. The 19th birthday is my first deposit. 20th birthday, I have a deposit of $2,500. 21st birthday, $3,000. I continue to do that on my 35th birthday. Well, let's see. On my 35th birthday, if I take 35 minus 18, that's 17. So I have 17 deposits. Therefore, I have 16 increases. So I'm going to have 2,000 plus 16 times 500 will be my last deposit. I think that's 10,000. You can check it and see. And so, we want to calculate the value of the symbol I, 2,000, 500, A, 17 at 4.2% interest. So we just want to calculate the value of that symbol. So we use a formula in the very first formula in the box above. It's 2,000 A17 plus 500 times A17 minus 17 times 1 over 1.042 to the 17th power over 0.042. So we have to do all that arithmetic. I would calculate the symbol first and put it in storage and do the arithmetic and confirm that you get $66,008.43. Okay, you might want to pause, make sure you can work your way through that example. You might want to look over this page before you go on to the second page and look at the rest of the video. So in the next example, we're going to see how these arithmetically increasing annuities just arise naturally from a reinvestment problem. Okay, so suppose this is example 3.9.9. 6,000 is deposited into an investment fund earning 6% annual effective interest at the end of each year. The interest from the fund is deposited into an account earning 4% annual effective interest. What is the balance of this investment at the end of 20 years? So in this case, I'm going to go ahead and kind of break things down. I'm going to look at our timeline. So we have time 0 and 1, 2, 3, 19, and 20. We have two accounts. We have an account that holds the principal payments. I'm going to call that the primary account. So we're going to have deposits in that primary account. The first deposit is 6K at time 1. Another 6K, another 6K. So we're going to make 20 deposits, one each year at the end of the year. And then these deposits, well, they're going to add up over time. So I can actually put the balance in the primary account on the second line. Don't have a balance at time 0. Have a balance of 6K at time 1. At time 2, all the interest is pulled out, and so the balance is just the sum of the two deposits, or 12K. At time 3, again, all of the interest is pulled out, so I just have my 6K plus the two other deposits of 6K, right? 18K. And here I have what? 19 times 6K, and then I have all 20 deposits in there. 20 times 6K, or what is that, 120,000? So this is the balance of my primary account at any particular time because I'm pulling out the interest at the end of each year. Then I want to take and determine how much interest I do take out. So at time 0 I don't have any interest. At time 1 I don't have any interest because I just made my first deposit. At time 2 I'm going to get 6% of this $6,000. And that's $360, but I'm just going to write it like this. Now, I also make my $6,000 deposit, so at time 2, my balance remains $12,000. I'm going to earn interest on this $12,000 balance at time 3, and so that's going to be what, 0.06 times my 12K, or 2 times 6K. And each year, I'm going to take and I'm going to earn interest on the balance from the previous year. The last time I'm going to earn interest is going to be on this balance here. So I'm going to earn 6% on that balance. So these interest withdrawals are being put into another account, into a fund that earns 4% interest. So we can view these as deposits into that fund earning 4% interest. So at time 20, I can write down the accumulated value of all of them. But notice the accumulated value, see 0.06 times 6K is 360. So they're increasing by 360. By 360 each year as well. So this is an arithmetically increasing annuity. 360 IS, and there are 19 of these deposits, and I'm using 4% to accumulate them. So that's how it would add up how much the interest payments have accumulated to in this second fund at time 20. It's easy to add up what's in the primary account, just 20 times 6K, or 120,000. Plus, I need to calculate the value of this symbol. So that's going to be what? 360 times, let's see what, 1.04 S19 minus 19 over 0.04. So I need to calculate that, and I think if you calculate that, you'll get $88,002.71. So this would add up to $208,002.71. Again, you might want to pause this and go back and look at the statement of the problem and look at how we've broken down the problem and make sure you understand it, because we went through it rather quickly. And make sure that you understand there are two funds. There's a primary fund, and then there's a fund that holds all the interest that's being withdrawn from the primary fund. And the interest that's being withdrawn from the primary fund is actually earning interest at a different interest rate. It's earning interest at a 4% interest rate. And then we calculate the value of the symbol. See if you can actually rework this example once you study it without looking at the paper. Make sure you can go through all the steps. This is an important problem. It shows up a lot, and it certainly will show up in a quizzing and testing situation for you. So you want to be sure and be able to work on it. Now, one thing I want to do here at the end, I'm going to go through this second, the last half of this sheet. Then there's a pen cast that will cover the third page. This decreasing annuity immediate is also in the pen cast, but it seems to be a little bit corrupted in the pen cast, so I want to go over it again in this video. So in a decreasing annuity immediate, we start out with a payment of n at time 1. We decrease by 1 the payment at time 2. We decrease it by 1 again, so we have a payment of n minus 2 at time 3. We can do this, and so that if we continue this pattern, we will have a $1 payment at time n. And then, of course, that will be our last payment, because it will go down to 0 by time n plus 1. So if we want to take the net present value of those payments at time 0, we give it this symbol, capital DA. And here we see formally what that is. You can tell that this is the net present value of those payments above. Now, to get the kind of the simplified version of this, I'd like to draw a picture of it. So that at time 1, I take this n dollars and I break it up into n $1 payments. I'm just going to stack those $1 payments on top of each other. And so let's say there are n $1 payments there. And then at time 2, I'm going to stack those $1 payments on top of each other. And there's one less. There's only n minus 1 of them. And at time 3, there is, again, one less than at time 2. So you get this kind of triangle-shaped stack of $1 payments over time. Let's see. At time n minus 1, you have 2 of them, and then at time n, you have 1. Okay, so there's a picture of all my payments and where they're made. And the reason I do this is because if I look across this row here, I have n $1 payments at the end of each period for n periods. Well, the present value of that is just an. Here I have n minus 1 of them. Present value of that is an minus 1. And I just continue this all the way up this triangle. Here I have what? A3, A2, A1. So that's the present value of the rows of my $1 payments. So if I add them all up, which I'll do over here to the right by using a sigma sign, So I'm going to use sigma k equals 1 to n a sub k. And then I can write down the formula for, I know what the formula for a sub k is. 1 minus v to the k over I. I can factor out my 1 over I and break my sigma up into two sums. I brought my 1 over I out in front. That leaves me with a 1, then minus sigma v sub k. If I add 1 to itself, n times, I get n. So it's 1 over I times n minus, and this is just the symbol ak. Excuse me, an. So 1 over I times n minus an. That's a handy formula to know. It's hard to do these decreasing annuity formulas just remembering the first formula that we derived at the very beginning. So this is one you'll want to know. Of course, to get a decreasing annuity due, we know the obvious thing to do. You just multiply the decreasing annuity immediate by 1 plus I. So you have what? 1 plus I times n minus an over I. Right? And then this 1 plus I comes down to the denominator, and you get n minus an over d, just like you would expect. The I turns to a d in the denominator. Likewise, you can sum these decreasing annuities or accumulate these decreasing annuities by moving the net present value forward in time to the last payment. And we do that by multiplying by 1 plus I to the n. So we have what? 1 plus I to the n times n minus an over I. So we have n 1 plus I to the n. And when I multiply the annuity immediate symbol times 1 plus I to the n, I get Sn over I. So this would be ds. Yeah. Again, I probably would just want to remember for the decreasing annuities, I'd probably just want to remember this first formula we derived and then move it around in time using compound interest as I need to move the value around. Okay, so again, there is a pencast called pencast. I think it's the second part of this, where you will go over some more examples, and so you'll want to do that just to see some more examples from this material, and we will go through some problems in class.